Hello, my name's Andrew Smith and I teach mathematics here at University College Dublin. Today I'm going to give you a taster of some of the things that you might learn if you come to study mathematics here. And I'm going to start with a problem about interpolation. And that means that you're given some data points and you're trying to find a suitable curve to go through those data points. The points that I'm going to pick today are the origin, x is 1 and y is 2, x is 2 and y is 1, and x and y both equal to 3. And I've shown here the simplest way that you might fit a line through those points. Of course, you can't fit one straight line through all of them. So here I've got 3 different line segments going through the points. And for some purposes, that might be good enough. But for other purposes, it wouldn't be. Quite often we need a curve that is smooth to go through our specified points. So here is one. This curve is called a cubic polynomial, and the coefficients there, the 11, the minus 9 and the 2, I've picked those so that they still go through, the curve still goes through the points I started off with. And now it's much smoother. And if we were, for example, solving some number theory problems, we might quite often find polynomials like this cubic polynomial are good ways of fitting through points that we're given. But this curve that I've fitted, it goes a bit wild outside my original range between 0 and 3. So it just seems to be going off to infinity very quickly here and to minus infinity very quickly here. And maybe you'd want a curve that didn't do that. So this is another curve. This here might be the kind of curve you'd use if you are analyzing waves. Maybe you're working to put musical works together and you're understanding the waveforms of sounds, or maybe you're working in clean energy and you're harnessing energy from waves and you need to model this sort of curve. So the red curve might be more suitable for that, and the green curve might be more suitable for other purposes in number theory or algebraic geometry. And then sometimes you don't want a smooth curve at all. Here's a history of the stock market in Ireland over the last 20 years or so. And you can see here that this doesn't seem to be a smooth curve. It wiggles a lot. And those wiggles are important. The fact that the curve is unpredictable is what means that so many traders are able to buy and sell, and nobody can really guarantee to make a profit. But some people get quite good at guessing, and we'll help you to understand that in some of our financial maths courses. And if you wanted to fit a curve that looks more like a stock market, you might use a fractal. This is a fractal, still goes through the same points. And what you can see here is that the areas that I've circled, they all look similar to each other. The same patterns appear over and over. And in fact, the same pattern within each circle is a scaled down and flipped over version of the whole curve, starting from 0 to 3. And for every little bit of the curve that you look at, it's actually a miniaturized version of the whole curve. And you'll learn how to construct those too. So to summarize what I've shown you, there's lots of ways of fitting curves through some points you're given. Sometimes you can join them by straight lines, and that's easy to do, but sometimes you want it to be smoother, and then you might use a polynomial or some sort of wave. And sometimes you don't want it to be smooth at all, and in those cases, you'd probably end up using something like a fractal.